Good afternoon and welcome to Quantum for Decarbonization session with Elvira Shishenina, quantum computing research scientist at Total, and Philippe Duluc, our big data and security CTO. You may use the Q&A function to post any question you might have for us. We will take time to answer these at the end of the session. Do not hesitate to visit our advanced computing booth to further discover our solutions. I will now leave the floor to Philippe for his presentation.
Thank you. Hello, everyone. So we will see today a quantum for decarbonization. We will address three topics. First one, just a summary of the Atos quantum strategy. After, we will see with a total use case for quantum for decarbonation. And after that, two announcements concerning the Atos quantum program. So now, what about the Atos quantum program? Since 2016, we have built a real end-to-end quantum ecosystem. We are selling a programming platform whose name is QLM, Quantum Learning Machine. It's a machine to learn quantum, which lets everyone to program, to optimize, and to test quantum algorithms. The test is made by simulation. It's a classical simulation, and this simulation is as realistic as possible. That means that we are simulating also the hardware, the qubits. Other thing in our program, we have developed a quantum consulting practice because more and more customers need to be helped, to be accompanied when they are exploring the quantum realms. And last topic concerning our program, but perhaps the most important one, we have planned to develop a quantum accelerator. That means a real quantum accelerator with qubits. And this quantum accelerator is planned for 2023, and it will be embedded in a hybrid HPC. So now we will see the ecosystems. You see that we have more and more customers using the QLM around the world. We have in US, we have a lot in Europe, and also Africa, Japan, India. And we have among these customers, we have universities, we have supercomputer centers, and we have also industry, a big group like Total, for example. And we have really created an ecosystem with the creation of the club. Club is our ecosystem for its QLM user group. It's our ecosystem for the QLM. We are gathering in this ecosystem users, customers, and partners. And the objective is for these users is to meet each other, is to share best practices, tips, and the advantage for Atos is to get feedback concerning our features and our technological roadmap. It's also a customer-driven program because we have two chairs. We have for Europe, we have Total, and for the rest of the world, US, we have the Oak Ridge Research Laboratory. Now, some element about the market. What is very important concerning quantum computing is that it is impacting all verticals in our industries. You know that Atos now is organized in verticals, and we are very happy with quantum because quantum computing concerns all verticals. We have practical use cases in each of these verticals. One of them is the resources and services, in which we have energy group, like a Total, and it is in these verticals that we are addressing quantum for decarbonation. Now, just some word about quantum for decarbonation, about the calendar. What is very important today, and it's a big change since 5 years, is that we are entering the NISQ era. NISQ stands for Noisy Intermediate Scale Quantum Computing. That means that we will have, in a very short period of time, in just several years, we will have small systems with a few qubits, between 50 qubits and 100 or 200 qubits, and without error correction. Why? It's because error correction is very costly, and we have discovered that it was possible to have quantum acceleration with noisy qubit. That means without error correction. And we will see with the example from Total how they are using this NISQ algorithm, variational algorithm, to get real quantum acceleration. Just perhaps a last slide to explain very well what is quantum for decarbonation. If I take this example given by BCG analysts, you see that on the slide that on the top left, we will have a very high impact at very soon. That means in the NISQ time. That means just several years with high impact. We will have the catalysts. And with this catalyst, we have an important use case. You see on the slide, it's carbon capture. Carbon capture is the example we have chosen with Total for R&D partnerships. And also, it's a very good use case in which Total is using the QLM to study the carbon capture. And now I'm very pleased to leave the floor to Elvira Shishenina from Total.
Thank you very much, Philippe, and thank you very much for inviting me and having me for this special day. So it will be true to say that our relations with Atos are quite long. I would say it's probably the oldest collaboration that we have and probably the most fruitful one regarding the young age of the quantum computing project in Total. So it started with purchasing a QLM machine in 2018. So from the beginning, it was of capacity of 30 qubit, and it was upgraded to 35 last year. And it practically became a foundation for all our, I would say, in-house development, and it gives us the possibility to develop, to train ourselves, and also to learn this complicated quantum technology, and while staying hardware agnostic before the best quantum technology will prove itself. So today I propose you some overview on our work in the domain of quantum chemistry, in particular the application for use case of CO2 capture by adsorption. So in quantum chemistry, the most probably interesting problem and the most complicated one is to find the ground state energy of molecular system. In practice, it corresponds to finding the lowest eigenvalue of the Hamiltonian operator in the electronic Schrödinger equation. So basically, why this problem is complicated, but just because to compute it in the exact manner, you need to take into account all the types of interactions between the particles inside this molecular system, and the number of permutations explodes exponentially with the number of particles that you have. So that is why this problem is considered as not tractable classically, but fortunately we have some advancement in the quantum field, and in particular the variational algorithms that Philippe already mentioned. In total, we have identified them. Two is variational quantum eigensolver and imaginary time evolution. I will speak about it a bit later. So variational here means that we converge to the exact solution while computing using classical post-processing, while computing the main characteristic energy on the quantum computer. So we have implemented the VQE solver in Total by using QLM, of course, and we to validate this implementation, we have created a set of molecules with increasing complexity, starting from hydrogen and up to dioxide of carbon. And we just computed the ground state energy using the VQE algorithms, and the results were pretty much interesting and quite nice, because we could achieve the error tolerance of 10-2 hard-3 with respect to a full configuration interaction solution, which can be considered as the reference one. So in this slide, I want to focus your attention on the fact that for computing the CO2 molecular, for us in that period took like the totality of the capacity of machine that we had in the beginning of 2019. and it was 30 qubits. So to advance in our simulations and to pass for solving more complicated use cases, we had to find some tricks in order to reduce the computational cost. And the idea is quite known and pretty natural, is that you can consider that the electrons which are close to the nuclei are in so strong interaction with the nuclei that we have a very few impact onto the interelement bonds. So you can practically freeze these orbitals, and as a result, reduce your computational space, active computational space. So here for CO2 molecular, we have freezed first 3 1s orbitals, and as a result reduce the computational cost from 30 to 24 qubits. The good news that we actually can go further in this strategy and freeze more and reduce more and more, but these actions must have at least some physical sense, as we say. And actually the procedure to efficiently approximate this active space, it is exist. So that's what practically was done for the next set of molecules. So here, this image shows how we can use the CO2 as a source of carbon in order to produce intermediate products in the energy transition chain, such as acids and aldehydes. So here, all numbers in red is the ground state energies in Hartree, which we are computed using the VQE on the QLM machine. And for example, for some of these molecules, we could move even up further in the complexity, such as, for example, for fumic acid here. So that was a pretty nice technique which we actively use now. We didn't stop on this. After computing the ground state energies, we also extended the VQE algorithm to computing of the excited states, the rest of the spectrum of excited states. And also we decided to profit such a nice feature as integration of a noisy environment into a simulation, which is available on QLM, and to see how the results of computation will behave in the presence of a noisy environment. And it gives to us an idea to create a sort of software package where we could reassemble all the benchmarks on QLM of the test on the molecules, as well as the notebooks. And it could be a nice tool, like to unite the quantum computing community to benchmark on the same test of molecules, different hour solvers and whatever the different platforms as well. So we will see later how to make it open source, this package. Okay, so this is all regarding the VQE. Yes, the second solver is much more sophisticated, I would say, from the point of view implementation. And to be honest, it's much less studied for us, for instance, but we continue to work on it because it has a lot of potential as well. It's called imaginary time evolution. It's a variational analogous of classical imaginary time evolution representing the real-time formalism. So here we are studying the thick rotation of a Schrödinger equation with the real time replaced by the imaginary one, which gives to us practically the possibility to connect the quantum physics with a statistical one, and being able to solve not only the ground state energy problem, but also a large class of the optimizational problem, to have an access to simulation of the dynamical systems, and I believe some kind of parabolic partial differential equations. So this method has a lot of potential, but it's much more complicated to implement. Just to give you a brief idea how it works, by using sum of projection operator, in the end you will obtain the system of the equation of the differential of equation on the internal angle, the parameter of your trial state that we call ansatz. And to compute this matrix A and vector C, you will need to compute a very complicated terms which involves the overlaps of the differential of the derivatives of your ansatz, and it imposes the additional complexity to this method, and that's probably why it's still less studied and interest not many people. However, once you have computed your matrix A and C, you could use a simple time evaluation procedure such as classical or first order finite difference scheme in order to evaluate your parameters from the initial one to the next one. And the idea is that if the initial state have a non-zero overlap with the ground state, by propagating your system through the imaginary time enough long time, you will converge to the ground state. And moreover, in the case of imaginary time evolution, you converge directly to the global minimum. And for example, in the VQ, sometimes you can fall in the local one. So that's kind of advantage of ETE with respect to the VQ. So for imaginary time evolution, we have implemented a solver and we have tested it, for instance, on the hydrogen molecule. The results are pretty nice, but it still must be optimized and generalized in order to make it more general for solving our use cases. So it's still under work. And yep, we still continue to work and in collaboration with Atos team in order to optimize and to study the scalability and to improve the scalability of all the solvers. So here are some important parameters that need to be improved. So here, for example, in the case of ET, you have a time evolution schemes. Why not to start to test something of higher order, like second order schemes or whatever? And in the case of the variational quantum eigensolver, you will have to work on the classical optimizers, which is also very complicated topic. Okay, so just to sum this up, as I said, we still continue to explore the solvers and continue to work on their scalability. And this is all in order to being able to exploit in maximum the resources that we have available now until the quantum technology is still evaluating. And for example, as you see in the exact example of the freezing orbitals for cost reducing, that was just a simple example of classical technique that we can use for simplifying our initial problem and make it tackable by the quantum means. But actually, we have in the disposal many of these classical techniques, and that's what is our primary aim. And also we converge in this opinion with the team of Atos, where we need not only explore the quantum technology itself, but also to keep serving the classical technologies which could help to us to prepare our complex problems until we wait for the capacity of the computers and also the error rates will be improved to prepare our problems and to solve them with the means that we have in disposal now. And this is the case of the CO2 capture by absorption use case. So this use case we prepared in collaboration with Cambridge Quantum Computing. And the main computation, for instance, the main simulations we perform on the QLM machine before probably realizing some realistic tests on the real computers. So it consists in study of the metal organic frameworks. So the unit cell of a metal organic framework is shown on this slide. It is involved with huge volume of pore in yellow, which is surrounded by the crystallic structure of metal clusters in blue, which are connected by the organic linkers. So thanks to the metal clusters, these types of materials, they attract the CO2 molecule. It interacts with the metal clusters first on the surface of this MOF, and it's entrapped, the CO2 is entrapped inside this huge volume of pore. Of course, these are very complicated structures to be tackled frontally, even by the classical means, especially that the classical methods such as DFT sometimes don't even converge on such structures because of high presence of the hydrogen bonds and like van der Waals types of interactions possible also. But these types of systems with high electronic correlations, they are actually would be the first candidates for showing the quantum advantage, because with the variational quantum methods, we can compute the electronic correlations exactly. So in this context, we don't study the entire MOF yet, but we decided to choose the realistic example of a metal cluster on the surface of MOS, since it's a principal actor in interacting with CO2. And in hoping that if we can improve the capacity of a metal cluster to attract better the CO2, we can improve the capturability and capture stability of entire MOF. So just to give you a couple of words on how we work on that, we just use the classical approaches like fragmentation and embedding scheme in order to decompose the big problem onto the small parts. And then we locally pass with a high precise and focused quantum methods on each part in order to compute the zones which are not accessible, for example, with the classical large-scale methods, and to improve the properties of these materials, hopefully, or to discover any of them. Okay, so this is just a brief overview on this use case. I probably let Philippe to continue, and yeah, thank you very much one more time. Yeah.
So thank you, Elvira. It's very promising. So the next slide. Okay, I will take the opportunity of this presentation to have two announcements concerning the Atos Quantum program. The next slide. So, first announcement, it's a recent improvement of the QLM with the QLM-E for enhanced. We have put GPUs, NVIDIA GPUs instead of CPUs, and this major improvement of the QLM because this has let us to obtain an improvement of a factor of 12. And this is great because it has been specially tailored for variational algorithm. This algorithm Elvira just mentioned before. So, and it is great for the NISQ era I have mentioned. The second announcement is exclusive. Next slide, please. We have announced today something which is very great and exciting in the field of quantum computing. The Atos Quantum team, has developed a quantum annealing simulator. And this is something which is very new. And we will put this simulator in the QLM. What is a quantum annealing? It's the second pass for quantum computing. The first pass, we know this pass for 5 years. It's the quantum circuit model with quantum gates, with a sequential quantum register. And the quantum annealing is something very new, which is efficient with a fewer applications. It's very dedicated for combinatorial optimization, with a famous example of the traveling salesman problem. And we have developed this new feature in the QLM. For the moment, we are entering a beta testing phases. That means we will work with selected customers and users to test this quantum annealing simulator. And at the end of the year, we will have a new commercial offer to offer this new feature to our customers, to the quantum ecosystem. This is a great news today, and the offer will come end of the year. Thank you very much.
Okay, thank you to Elvira and Philippe for their great presentations. So we've been receiving some very interesting questions through our Q&A tool. So I think we can begin with the first one. How do you determine which problems are suitable for quantum? So that would be for Elvira.
Yeah. So thank you for the question. In the case of quantum chemistry, I would say it's kind of the ground state energy problem. It's kind of very well suited, naturally suited to be solved, because the problem, the fermionic problem can be, the fermionic Hamiltonian can be like the problem can be represented in the equivalent form, which is called second quantization. And it will be written in the terms of creation and annihilation operators or on the spin electron, on the spin orbitals with different numbers, which will provide you like the information about if the electron was created or not. So thanks to this equivalent form, you have sort of the parameters, characteristics, which have this binary interpretation, and this operator, thanks to the transformations such as Brauch-Taif or Jordan-Wigner, or I believe there are any others, can be decomposed in the basis of the Pauli matrices, of the Pauli operators, which can be considered as a basis for our quantum computation. So like that, we can transform our fermionic initial Hamiltonian into a qubit Hamiltonian and to enter it into the quantum computing. So, but basically the problem of state preparation, it's quite common for all the quantum scientists. So every time you should work on the possibilities how to encode your initial data into the quantum way to be able to solve the problem on the quantum computer. So no, it's not very simple question, but yes, there are a lot of work and a lot of people who work on this. So, yeah.
Okay, thank you, Elvira. Another question that we received was about the use of the QLM as a production tool. So that would be for Philippe Duluc. Can it be used as a production tool?
Yes, I think the first usage of the QLM is to learn quantum to prepare the future. It's not a production tool today. For most of our users, our customers. But we can say that for some people, it's really a production tool today. For scientists, for researchers, for example, they are studying physical problems, they are publishing scientific papers, and they use today the QLM to help them in their researches. We can say for science, it's today a production tool, and for industry, we think that we have to wait some more years to wait for the NISQ accelerator. It will be a production tool in the next year, not today.
Okay, thank you, Philippe. And also, I think we've got some interest for the QLM user club. Can anyone join this user club?
Alors, the user club is a club for the users of QLM. In these users, we have various type of people. We have the customers. We have also partners. And we have, for all customers, for example, a supercomputing center, for a university, you have a large amount of people able to access this QLM. And all these people, the students, the partners of the supercomputer center, can participate in the user group. And perhaps an information I forgot to mention is that the kickoff of our user club was 5 days ago. It was a great success with almost 50 people coming from 20 organizations, and among this organization, you have, for example, Rolls-Royce. Rolls-Royce has not got directly a QLM, but used the QLM of a supercomputing center of R3 in UK. So you have just to be a user.
Thank you very much. So we will take one last question. One of them was about the quantum annealing simulator that you just mentioned. Would it be possible to have detailed technical information on the machine and a comparison with a real quantum annealer?
As I told you, it's just the beginning of the experimentation. We are, if a company is interested in testing this new simulator, they have just to ask us. We will begin the experimentation to test this simulator on use cases and so on. So welcome if you are interested in testing.
Okay, thank you very much, Philippe. Thank you all for being in our live session about the use of quantum computing for decarbonization. Don't forget to visit if you're interested to know more about our advanced computing solutions. We have an online booth on these topics, and the recording of this session will be available online for you to look back at. Thank you very much.